and we'll get started. So last day, we did a whole bunch of stuff about current and resistance in circuits. We talked about batteries and the EMF of a battery. Does anybody have any questions before we get going for today? So we're gonna do more on circuits. So I thought I would put in this slide that gives us all the information about drawing circuit diagrams. When we talked about capacitors as a circuit device, we did a little bit. We said that the straight lines are just pieces of wire, conductors with no resistance, so ideal wires. Our capacitors are represented by two parallel lines. That's a capacitor. Our battery has a long line for the positive terminal, short line for the negative, and resistors are a squiggly line. People probably know this from high school when you did circuit diagrams in high school. When we have internal resistance, that's labeled with a little r. We talked about that last time. That's what's happening inside the battery. These two devices, the circles with A's and B's in them. So when you were in the lab, you measured stuff using the little yellow meters. Those were called multimeters. When you use them to measure voltage, we call them voltmeters. When you use them to measure current, we call them ammeters, and they're represented by V's and A's in circles. And we're going to talk about the functions of those devices eventually. So, next, we'll just finish up a couple of examples from last time. So last time we talked about the battery. So here, let's just look at a simple circuit. Let's say we have two cases. Let's say we have an ideal battery with no internal resistance. That will be hooked up to a 50 ohm resistor. Or let's say we have a real battery with some internal resistance, and we hook that up to the same 50 ohm resistor. For each case, what current do we draw out of the circuit? So what current do we end up with if there is internal resistance or is not internal resistance? And what is that potential VAB if we do and don't have that resistance? So I hook up the battery to the circuit. This potential is 1.50 volts. Current will start to flow, comes up, goes through the resistor, around the circuit, back into the battery. So that's the current flow in that simple circuit. The potential difference across points A and B, the only thing that's supplying the potential is that ideal potential of the battery. That's called the EMF, equals 1.50 volts. Okay, so there's the potential between points A and B. You can sort of think of this potential kind of on the inside or the outside. If you look at what's happening in between A and B, we only have that battery in there. If you look at what's happening on the outside, then that's the potential across the resistor. So you can sort of look at it two ways. It's either the potential across this outer loop or the potential across this inner branch. Same deal, right? Potential is the potential. If we want to find the current, we'll use our Ohm's law. The current is going to be the potential divided by the resistance, 1.5 volts divided by 50 ohms, to get 0.030 amps. So that's a really simple analysis. We're going to do more complicated ones. Let's look at our one with the internal resistance. So our battery should still supply an ideal potential of 1.5 volts, but this one has some internal resistance, and that amount is 2.5 ohms. And we're still connected to the 50 ohm resistor. So we want to find two things. We want to find the potential across points A and B, and the current through the circuit. So once we hook up the battery, current does start to flow around the circuit like this. For our potential across the battery, VAB, we can look at it two ways. It's either the potential across the inside, so that's going to be however much the battery should supply, take away what's used up by the internal resistance. Or if we look at it from the outside, it's the current times the resistor on the outside. So this potential is across the resistor, so this potential is equal to I times R. And these are things we wrote down last time. Now we're just putting them in examples with numbers. So if we look at this part of the equation, we can certainly solve for that current. So our current is EMF divided by the sum of the resistances, 0.0286 amps. If we stop and look at this answer, this makes sense, right? If our battery has internal resistance, we get a lower current output by that battery. It's not as good as doing its job when it has an internal resistance. And then the potential, VAB, equals I times R, equals 1.43 volts. Okay? And we also get a reduced potential across that resistor. That makes sense too. When you have batteries and they're getting old, they start to die. The current gets smaller and the potential gets smaller, and that's when you know you have to get new batteries. Okay, so the impact of that internal resistance is to lessen the potential and current output. Probably most of the problems we do are going to assume zero internal resistance, but it's still important to understand how it works. Okay, questions? All right, next we'll talk about power in circuits. We talked about power when we did our wave section, and we said that power is the change in energy divided by the change in time. It's the rate of energy delivery. So we can write down power is change in energy divided by change in time. Power uses a symbol of a capital P. It's got units of watts, which is a capital W, where a watt is a joule per second. And that's after the Scottish inventor James Watt from around 1800. So in terms of a circuit, power is the work, or the change in energy, divided by the change in time. The work done in an electrical circuit is given by the change in potential energy. So we've got Q times the change in potential divided by delta T. So if we look at this expression, Q divided by delta T, that's how we defined our current. Power equals current times potential difference. So if you're trying to find the power supplied to a circuit or used up by the circuit, you do current times potential or voltage, and that gives you your power. Sometimes you would write power equals I times V instead of the delta V. Kind of means the same thing. Okay, any questions? Then you can do a very small derivation. If you remember that V equals IR, you can get two new expressions for power. So I'll leave that to you to figure out. Of course, I will show you the answer, and then we'll do a power example. Or I'll post the answer. Okay, so let's go back to that example we just did. And let's find the power supplied by the battery in each circuit and the power dissipated in the resistor in each circuit, and we know the internal resistance is 2.5 ohms. The resistors are 50 ohms. And that EMF is 1.50 volts. So we'd like to find the power dissipated in the resistor. So the power is equal to current times potential difference delta V. And one of the expressions you can get is current squared times resistance. So if we want to know the power dissipated in the resistor, we can do I squared R, and we'll find the power. The current we already found was 0.30 amps. Square that times 50 ohms. And we get a power of 0.0450 watts. Okay, so there's the power. You can also find the power dissipated in this resistor, doing the same deal. Power equals I squared times R. The current this time was 0.0286 amps. Square that times 50 ohms. So the power dissipated in this one is 0.0409 watts. What's kind of interesting about this, we see that there's less power dissipated in this resistor. So what happens in systems is that the battery puts energy into the system, and energy gets dissipated through resistors. The way it gets dissipated is through heat. So in this system, there's a lot of energy getting dissipated through this little internal resistance. So the power in this guy is going to be I squared times this resistor. That there's power dissipated in the battery means the battery gets hot. Okay, so when you have old batteries and you hook them up to a circuit, you're going to notice that they heat up real quick. That's because as the current flows, it's using up a lot of energy. So this battery would end up getting hot because it's dissipating energy. Questions? Okay, so that's the end of the very short chapter 25.
Isn't that also how a light bulb works? It runs through a resistance and that produces the light and heat?
Yeah, exactly. So if this was a simple light bulb circuit, we'd have a battery here hooked up to a light bulb. The light bulb has a filament inside, which is just a resistor made out of tungsten or something. It heats up, it emits energy. It emits energy as heat and light, and yeah, that's how a light bulb works, is the current going through the resistor in the filament in the light bulb. Yeah, good application. Yeah.
For the second circuit, when we are trying to find out the power, we are not taking like the internal resistance.
Oh, I just didn't bother to do it right. We were asked to find the power dissipated in the resistor. That was kind of the only part of the problem I did. Find the power dissipated by the 50 ohm resistor in each circuit. Sort of decided on the fly, the rest of it wasn't very interesting. Okay. So that takes us to chapter 26. We're sort of close to the cutoff point to the test, but we're not there just yet. I'll kind of let you know when we hit it. Probably it'll be today, but it might be the first little bit of Monday. So if you downloaded the notes, I fell victim to lazy cut and paste. This says capacitor and capacitor. This is all about resistors. So kindly scribble out the word capacitor and fill in resistor there. It's what it should be. So we're going to talk about resistor circuits. You've done this in the lab already. That was the last experiment. So here's what you were doing in the lab. We can combine resistors the same way we can combine capacitors. So we talked about capacitors in series, parallel, and combinations. We're going to do the same thing with resistors. We're going to apply the same sort of analysis to figure out how do we find equivalent resistances in different kinds of circuits, and what does that mean about currents and potentials. So that's kind of where we're going with this. So the first thing we'll talk about is resistors connected in series. And in series means they're all connected in a line or in a row. So if you want to figure out if two resistors are connected in series, draw the current in the branch. So this battery is going to put out some current I. This current has to stay in the wire because it can't go anywhere else. The current goes through R1, then it has to go through R2, then it has to go through R3, and it comes back around into the battery. If the same current has to go through it because there's nowhere else to go, that means it's in series. So they all have the same current flowing through them. If they all have the same current, then it means that this potential delta V, that's the potential put into the circuit, it has to get used up by the three resistors. It has to be divided over the three resistors. So they all have the same current, and the potential is divided over the resistors. And we use this same line of thought when we talked about capacitors in series. We said that the potential is divided over the capacitors, so same deal here. If our potential is divided, it means delta V, the amount of potential supplied to the circuit, is going to be equal to the potential across the first resistor, delta V1, plus the potential across the second one, plus the potential across the third one. So that's how the potential is going to get divided. Here we might remember Ohm's law, V equals I times R. So the potential across resistor 1 is I times R1. Potential across resistor 2 is I times R2. And the potential across resistor 3 is I times R3. Okay, so we just put in our statement of Ohm's law there. So just like in our capacitors, we can construct a new circuit where we take out the 3 resistors, we put in a single resistor, and it gives us the same current for the same potential. So we can make a new equivalent circuit, and it means we hook up that resistor to this battery, and we get an identical current I. So we can make an equivalent circuit. So we get the same I for the same potential delta V when we use R equivalent, just the right value. So this tells us that delta V is equal to the current times R equivalent in this circuit. So our total potential is the current times this resistance. We can put this result in this equation down here. And then when we look at that equation, we see that we have current in every single term, so we divide both sides by I. And we're left with an expression that R equivalent is equal to R1 plus R2 plus R3. So this is our expression for equivalent resistance for resistors connected in series. Questions? So when I was a kid and we had Christmas lights, I think it's different now, pretty sure it's different now. When one light would go out, the whole strand would go out. Sound
Still
familiar
like
to
that.
anybody? Yeah, lots of them are still like that. So if one goes out, means they all go out. That means all those lights are connected in series, right? Which is why then you had to go through every single bulb, finding the one that was blown to put in the new bulb. So lots of lights now have them connected a different way, and we'll get to that different way soon. So that's just sort of one impact of things connected in series. If you bust one resistor, you've got an open circuit and the current can't flow because it can't travel through air. Okay, let's do an example. So let's have 3 resistors connected in series, and let's do a simple analysis. Let's find the equivalent resistance. Let's find the current and the potential for each resistor. So let's start with the equivalent resistance. We might start by drawing the equivalent circuit. So our equivalent circuit would have our 9-volt battery here. We would take out those 3 resistors. We would put in an equivalent resistor. And both of those circuits would draw the same current I. Okay, so we have an idea of what we're doing now. We'd like to find the equivalent resistance, so we can go ahead and use the equation that we just came up with. R equivalent for resistors connected in series is just the sum of the resistances. So 15 plus 4 plus 8 equals 27 ohms. So that equivalent resistance would be 27 ohms. So now, if we'd like to find the current through each resistor, if we come down and we look at this equivalent circuit we drew, that R equivalent is 27 ohms, we can apply Ohm's law to this circuit. We know V equals I times R. We should be able to calculate that I value. So I is delta V divided by R equivalent, 9 volts divided by 27 ohms, get 0.333 amps. So that's the current going through both the top circuit and the bottom circuit, because they are equivalent. So that's our answer to B. Because these are in series, they all have the same current, so they all have a current of 0.33 amps. Because they're connected in series. Part C, our potential across each resistor. So we want to do each of the 3 resistors. So for our 15 ohm resistor, the potential across that one is going to be the current, 0.333 amps, times the resistance, 15 ohms. So we're going to use V equals IR here. Gives us 5 volts. The potential across the 4 ohm resistor, delta V, is going to be our current, 0.333 amps, times 4 ohms, to get 1.33 volts. And across the 8 ohm resistor, delta V is the current, times 8 ohms equals 2.67 volts. And then if you added up those 3 potentials, you'd see that they added up to be 9 volts. All the potential is evenly distributed. Questions? So that's our resistors in series. So we can also connect our resistors in parallel. We do that physically the same way we connected the capacitors in parallel. So you take one set of leads off the first resistor, plug them into the battery, set of leads off the second resistor into the battery, and a set off the third resistor into the battery. They're all hooked up directly to the battery, so they all have the same potential. So that's our defining feature of resistors connected in parallel. Another way to sort of tell is if there's sort of nothing in between them, right? If they can be adjusted so they meet at a common point, they look like they're in parallel then. It's like another way to tell. So resistors connected in parallel are joined top to top and bottom to bottom, and they all have the same potential difference. So that's the defining characteristic of resistors in parallel, and also capacitors in parallel. Things in parallel have the same potential. If we think about what happens with the current comes out of the battery here. So there's our total current I. When the current gets to this branch, it has a choice. It has 2 wires it can flow through. So the current will flow through each wire. Some current will flow through each wire. The part that goes down through resistor R1, typically we call that I1. So some comes down, some comes across. Of the stuff that comes across, it has a choice when it hits this spot. It can either go forward or it can move down. For the current that moves down, we'll call that I2. And the current that went forward, we'll call that one I3. Okay. So the current has to split over the 3 resistors. Okay, because we can't lose current anywhere. We have to have the same amount of current, so it divides over the 3 resistors. The current splits over the resistors. To say that the current splits, the total amount of current put out I is whatever ends up through 1 plus whatever ends up through 2 plus whatever ends up through 3. So there's our resistors in parallel. And here we might put in our Ohm's law that current is going to be our potential delta V divided by our resistance. So there's how we can write down the current in the circuit. Just like the stuff in parallel, we can create a single equivalent circuit. So we can do an equivalent circuit. In this circuit, we take out these 3 resistors, we put in a single resistor, and we get exactly the same current. Okay, so equivalent circuit still means the same thing. So delta V equals I times R equivalent, our equivalent circuit, which means that our total current I delivered would be delta V divided by that equivalent resistance. We'll put that in down here in this equation. You see that we've got delta V in every term on both sides, so we can divide through by delta V. Then what we're left with is 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. So this is our equivalent resistance for resistors connected in parallel. If we come back to our Christmas lights example, if one of the lights blows, if this circuit breaks, we won't get current through this branch anymore, but we'll still get current through the other two branches. Okay, so if you have circuits where you don't want everything to go at once, then you would have a parallel connection, at least for the branch that you don't want to blow. Okay, questions? Again, I'll just stress a little bit that the equations for equivalent resistance and capacitance, they're sort of flipped, right? We do the reciprocals for resistors in parallel or capacitors in series. We add them straight up for capacitors in parallel or resistors in series, so make sure you don't get those equations confused. So let's take our same three resistors, let's put them in parallel, and let's find the same answers that we did last time. So if we wish, we can go ahead and draw that equivalent circuit. We've got our 9-volt battery, our equivalent resistance. Delta V is still 9 volts. And if we think about the currents in each circuit we put out the same current I. In our parallel connection, that current I is going to split. So some current goes down through the 15 ohm resistor, I1. Some current goes down through the 4 ohm resistor, I2, and some current goes down through the 3 ohm resistor, I3. Okay, so that's the nature of what's going on with those currents. First part of the question asks, find the equivalent resistance. So for part A, we know that 1 over R equivalent equals 1 over 15 ohms, plus 1 over 4 ohms, plus 1 over 8 ohms. If you like your fractions, you'll probably find a common denominator and add them up fraction-wise. For these, I'd probably go to my calculator to see that that's 0.442 ohms to the minus 1. Take the reciprocal of both sides, and we find R equivalent is 1 over 0.442 ohms to the minus 1, or 2.26 ohms. So our equivalent resistance is pretty small in this circuit. Part B, let's find the current through each resistor. Actually, why don't we go ahead and do part C first. Part C says find the potential across each resistor. They're all the same because they're connected in parallel. Part C was easy to answer. Now that we've got C established, it'll be easy to find the current through each resistor. That's just going to be using Ohm's law. So through the 15 ohm resistor, we're going to use delta V equals IR, which tells us that I is delta V divided by R. So through the 15 ohm resistor, the current is going to be delta V, 9 volts, divided by the resistance, 15 ohms, to get 0.6 amps. Through the 4 ohm resistor, current is 9 volts divided by 4 ohms, 2.25 amps. And through the 8 ohm resistor, current is 9 volts divided by 8 ohms to give us 1.125 amps. If we're looking at these currents here, we might notice that the biggest resistance has the smallest current, and the smallest resistance has the biggest current. That makes sense if you think about how resistors work. So resistance means resistance to current flow. The 15 ohm resistance, it has a big resistance. It's hard for current to get through, so less current is going to go through that branch. The 4 ohm resistor, that R value is small. It's easy for current to go through, so more current is going to flow through that branch. So physically, you can check your answers to see that they make sense that way. Okay, so that's resistors in series and parallel. Then we have combination circuits. So there are two ways to deal with combination circuits. I'm only going to do one of them using the equivalent resistance method. Then we're going to move on to Kirchhoff's laws, but we'll go through this first. Just to recognize that you can always do this sort of analysis with series and parallels, but we're going to spend most of our time focusing on Kirchhoff's laws because it's maybe a little bit more general and more useful in the long run in the big picture. So got the same question, we've got the same 4 resistors, but we've connected them in a slightly different way. We want to find equivalent resistance, current for all of them, and potential for all of them. When we have these combination circuits, we deal with them the same way that we did for the capacitor circuits. We look for obvious parallel or obvious series, and we deal with them one bit at a time. So we have to look at our circuit and we ask, are any of these in series or are any of these in parallel? I'm going to say that none of them are in series because there's no 2 resistors that are joined by a straight line. Okay, so there's nothing in series. Let's see if anything are parallel. So this 4 gets connected to these 2 dots. So 2 sets of wires go down to these 2 dots. This 8, that's got a couple of sets of wires that go straight to these 2 dots. These 2 resistors are hooked up to exactly the same points. These 2 are in parallel. So the 4 and the 8 are connected in parallel. So that's the first thing that stands out at us. So this branch is a parallel connection. We know that parallel means same potential. So we can find our R equivalent here. 1 over R equivalent is 1 over 4 ohms plus 1 over 8 ohms. So that's the same as 3 over 8 ohms. So our R equivalent is 8 ohms divided by 3, or 2.67 ohms. Okay, so we've dealt with the first connection. After we deal with the first connection, we draw a new diagram. So I've got my 9-volt battery here. That connects to my 15 ohm resistor, which now connects to the equivalent between the 4 and the 8, the 2.67. Now we ask for the next identifying feature, how are these 2 connected? These are right in a row. The current comes out here, goes through the 15, then has to go through the 2.67. These 2 are connected in series. And series means they have the same current. For a series connection, we know R equivalent is equal to the 2 resistors just added up, 15 plus 2.67, 17.67 ohms. So we'll finish by drawing one last equivalent circuit. This will be our answer to part A. There's our 9-volt battery connected to an R equivalent of 17.67 ohms. Okay, questions? It's pretty straightforward. Okay, so you just do them one at a time, series and parallel. So next, and this one we're going to have to be a bit more methodical. We're trying to find the current through every resistor and the potential across each resistor. So now what we have to do, and we did this with the capacitors as well, we basically have to work backwards. We have to start with this circuit. We have to figure out current and potential. We come back to this one for current and potential, back to this one for current and potential. So we work forward to find equivalent resistance, then we start to work backwards to find all the currents and the potentials. So I could draw on this, but I don't wanna mess up this diagram. I think I'm gonna start my diagrams fresh. So we'll start with this one. So I've got a 9-volt battery connected to a resistance of 17.67 ohms. If I look at this, I know that current is gonna flow through that circuit. And I know that I can use Ohm's law of V equals IR to find that current. So I'm gonna do that for this step. So I equals V divided by R, 9 volts, divided by 17.67 ohms. My current running out from that battery is 0.509 amps. Okay, that step's really straightforward. Now what we have to do is back up a step. Okay, so we have to ask, where did this circuit come from? And what does that tell me about that circuit, where it came from? So this circuit came from, or was an equivalent of, whatever sort of language you prefer here. We had the 9-volt battery, and that was connected to the 15 ohm and the 2.67 ohms. So this circuit is the one we simplified to get here, so we're working backwards. And what we know is that this 17.67 was a series equivalent of the 15 and the 2.67. Here we might also remember that series means same current. If series means the same current, then we can label that current on this diagram. So that current I comes up through here, goes through this one, goes through this one. So there's our current I equals 0.509 amps. We know the current through each of those resistors. We can find the potential across each of those resistors. So this 15 ohm has 0.509 amps. This one has 0.509 amps. For the potentials of each of them, P equals IR. So for the 15 ohm resistor, the potential is the current 0.509 times the resistance 15 amps to give us a potential of 7.64 volts. Sorry, I'm just realizing how small my handwriting is probably getting. So that's hopefully easier to see. So now I know the potential across the 15 ohm. I can also find the potential across the 2.67. V equals current 0.509 amps times 2.67 ohms equals a potential of 1.36 volts. So that's my potential across this one. When you're doing an analysis this way, it can be helpful to write everything right on the diagram so that you're not getting confused by stacks of numbers off on other places. If you put them on the diagram, then you're keeping it all together and hopefully you wouldn't get as confused. So we've answered our question, what's going on with the 15 ohm resistor. That one's all done here in this part. Now we have to figure out what's going on with the 4 and the 8 ohm resistor. So we have to remember, where did the 2.67 come from? 2.67 was the parallel combination of this one, so we have to back up a step.
So rather than doing Ohm's law for both of those resistors, could we have simply just done it for one and then subtracted that number from the total?
Yes, you could have done that as well. You would have known that the potential on this one was 9 minus 7.64. Yeah, that's fine too. Okay, so we're going to back up one more step. So this one came from, we had our 9 volt here, our 15 here, we had our 4 here, and our 8 down here. So that was our 15 ohm. We already know everything about that one. That's our 9 volt. This one is a 4 ohm. This one is an 8 ohm. And what we know between the 2 and the 4 and the 8 is this one is the parallel equivalent. Parallel means same potential. So we know that the 4 ohm resistor has a potential of 1.36. And the 8 ohm has a potential of 1.36 volts. That's because the 4 and the 8 make a parallel equivalent of 2.67. All of those things have to have the same potential. Then if we want to find our currents, we use our Ohm's law. So for a 4 ohm resistor, V equals IR, I equals V divided by R. So our current is equal to 1.36 volts divided by 4 ohms, gives us a current of 0.34 amps. And then we can do likewise with the 8 ohm resistor. I equals V over R. 1.36 volts divided by 8 ohms gives us 0.170 amps. So there's the current and the potential through and across each of the 3 resistors in that circuit. Okay, any questions? No, okay, so the very next thing we're gonna do is start Kirchhoff's laws. I'd rather not start with 3 minutes left, so we'll pick up there on Monday.